Welcome back to Science Corner. For all of us amateur scientists out there who love to keep up with, well, the really cool stuff that's happening in science, even if we, aren't working in a lab ourselves.
Right, right.
Today, we're taking a deep dive into something that really sparks the imagination. It's called SimCity, and it's all about building these huge, explorable 3D worlds automatically.
Yeah, it's exciting stuff for sure. I'm glad to be back to chat about it.
So before we get into the nitty-gritty, can you just set the stage for us a little? I mean, creating these massive virtual environments, whether it's for games, VR, or even simulations, it's a pretty daunting task, right?
Oh, absolutely. Traditionally, it's been a hugely labor-intensive process. You're talking about massive teams of artists, designers, spending countless hours just to build these environments by hand.
Yeah, and it's not just about placing a few objects here and there. It's about crafting these believable worlds with intricate details.
It is. That's why Sin City is such a game changer.
Yeah. Right, because what if you could just describe the world you want, whether it's, I don't know, a futuristic cityscape, a dense jungle, whatever, and have it generated automatically. That's what Sin City is trying to do, right?
Exactly. The idea is to create these expansive 3D worlds from simple text prompts, and here's the kicker, without any specific training data.
Without training data. So we're not talking about an AI that has to learn from a massive database of existing 3D worlds.
No, it's completely training-free and optimization-free, as the researchers call it.
Wow, okay, so color me intrigued. How does it work?
The real magic lies in how SimCity brings together different types of AI that are already really good at what they do.
Interesting.
We're talking about pre-trained 3D generative models, which are amazing at understanding spatial relationships and creating these solid 3D structures.
Right.
And then we have 2D image generators, which have become so powerful at creating those visually rich and detailed images, all from text descriptions.
Yeah, the progress there has been incredible.
Oh, it has. So SimCity is like a marriage of these two, combining the spatial understanding of the 3D models with the artistic skills of the 2D generators.
Fascinating. But how do they actually build a whole world out of that?
Yeah.
I mean, you can't just generate everything at once, right?
No, that's where the tiled part comes in. Instead of trying to create this massive, sprawling world in one go, they break it down into smaller, more manageable chunks.
Ah, I see. Like building blocks?
Exactly. Imagine a giant mosaic where each tile is a detailed 3D scene.
Okay, I can picture that.
And these tiles are generated one after the other sequentially. And here's the crucial part. Each new tile takes into account what's already been created around it.
Ah, so it's not just randomly placing these tiles. It's building them with context.
Exactly.
Yeah.
And because it's done step by step, it doesn't require this crazy amount of computing power, even for huge worlds.
That makes sense. So it's like building a massive landscape puzzle piece by piece. But each piece is already a fully detailed scene.
That's a great analogy. And this approach gives the creators so much control over the layout and the look of the world.
You can basically guide the AI as it's building, right?
You got it. With text prompts that are specific to each tile.
Wow. I'm already impressed.
Yeah.
So help me understand this a bit better. What were the limitations of the older methods for generating these 3D environments? Why was SimCity needed?
Well, a lot of the older 3D models were what we call object-centric.
Really?
They were great at making individual 3D objects, a table, a car, a tree, but they weren't so good at figuring out how to put those objects together in a natural way.
Ah, so you might have these beautiful, highly detailed 3D models, but actually building a city or a forest out of them was still this huge manual task.
Yeah, exactly. You needed artists and designers to arrange everything, make sure it looked believable and all that. Then you have the image-based methods.
And those were different.
Oh, yeah. Those tried to turn a 2D image into a 3D scene. They'd use algorithms to predict depth from the image and then use powerful 2D image generators to fill in the details, sometimes using representations like NeRF or 3D Gaussian splatting, which are basically ways to store and recreate 3D scenes.
So it's like taking a photo and then having the AI imagine what's beyond the edges of the photo and create it in 3D.
That's a great way to put it. And systems like World Labs have gotten really good at this. But the problem is, you can only explore so much of that generated world. It's more like a bubble around the original photo.
So it might look amazing from a single point of view, but if you try to walk around, it all falls apart.
Yeah, kind of. Think of it like trying to walk into a painting. You can look at it, but you can't actually explore it.
Right, right. So those image-based methods were great for creating those stunning snapshots. but not so much for building explorable worlds.
Exactly. Then there's the purely 3D generative models like block diffusion and LT3SD.
And those were better at creating those large, internally consistent spaces.
They were, but they often lacked the visual quality and diversity that you could get from the image-based methods. And that's because they weren't trained on those massive image datasets that the 2D generators had access to.
So it was a trade-off, 3D coherence, but simpler visuals, or amazing visuals, but limited exploration. That's where Sin City comes in, right? It brings the best of both worlds.
Exactly. It combines the structural understanding of a 3D generative model called Trellis with the visual power of a 2D image generator called Flux.
Clever. Okay, let's get into the details of this tile-based approach. How are these tiles actually organized, and how do they fit together?
Well, picture it like a chessboard, a grid of square tiles.
Okay, that's pretty straightforward.
And these tiles are generated in a very specific order, usually row by row, so that as each new tile is being created, the AI knows what's already been built next to it.
That's the context we were talking about.
Exactly. And each of these tiles can be pretty complex on their own, with multiple objects and the ground surface itself. It's not just basic shapes.
So a single tile could be a park, a section of a building, a courtyard, that sort of thing.
Yeah, exactly. And all these tiles are then seamlessly stitched together.
This is sounding more and more impressive. Let's break down these three main steps you mentioned. A 2D prompting, 3D prompting, and 3D blending.
Sounds good.
Starting with 2D prompting, how do you go from a general description of the world to instructions for creating these individual tile images?
Okay, so you start with that high-level prompt, say a futuristic city with flying cars. And then you use a language model, something like ChatGPT, to break that down into more specific prompts for each tile.
So the language model is like the world-building assistant.
Yeah, kind of. It helps to translate that broad vision into more manageable instructions while still ensuring everything has a consistent style. Figure 13 in the paper shows an example of this. You can see how the general prompt gets divided into detailed descriptions for each tile, like a skyscraper with glowing windows or a traffic intersection with flying vehicles, and then those are all tied together with a global style prompt like futuristic, nighttime, neon lights, something like that.
Wow, so it's really using AI to organize the creative process.
It is. And then these tile-specific prompts are fed into the 2D image generator, which is Flux in this case, but they use some really clever tricks to make sure those 2D images will work well for 3D.
Like what?
Like, they condition the image generation on a base image and an in-painting mask. Take a look at figure 4 in the paper. The base image is just a simple gray shape, and the mask highlights a specific area on top of it. By providing this kind of framework, they make sure the generated images have a consistent perspective and shape, which makes them much easier to turn into 3D.
Ah, so it's like giving the AI a template for each tile so it doesn't go off the rails.
Right. Otherwise, you might get all sorts of weird angles and perspectives, and then it would be impossible to build a cohesive 3D world.
So it's all about setting up the AI for success right from the start.
Exactly. And then, for all the tiles after the first one, they incorporate context from the neighboring tiles.
Yeah.
They actually render the existing 3D world into that base image so the 2D generator can see what's already there, as seen in figure 5.
So if you're generating a building next to a road, the AI will know to make the building actually connect to that road.
Yep. And they even trim any tall buildings from the existing scene before rendering it to make sure the ground levels match up, as shown in figure 6. They don't want a skyscraper from the next tile obscuring the ground where the new tile needs to be placed. And then for tiles on the edges of the world, they might temporarily duplicate a nearby tile to provide context, as mentioned in Appendix A.2. It's really clever how they handle all those little details.
It is. Okay, so now we have all these 2D tile images. What happens in the 3D prompting stage?
This is where they use Trellis, the 3D generative model, to turn those 2D images into actual 3D geometry. But before that, they do some image processing, what they call 2D foreground extraction and rebasing.
Let's break that down.
Okay, so using that in-painting mask we talked about, they isolate the specific part of the 2D image that represents the new tile, as shown in figure 7.
They cut out the new tile's content from the larger contextual image?
Yeah, that's it. And then comes rebasing, which is super important. They basically add this slightly larger gray slab underneath the tile in the 2D image. See, it helps Trellis to create a more solid 3D model that sits correctly on the ground plane. Plus, it gives them this clear base that they can remove later on. Figure 8 really shows the difference it makes.
So it's like giving the 3D generator a foundation to build on.
Precisely. Then, once Trellis has created the 3D model, using something called 3D Gaussian splats. They do a quick check to make sure the tile is the right size, roughly square-shaped, and if the base was reconstructed properly.
Quality control.
Yeah. And if it doesn't pass the check, they just regenerate it with a slightly different random seed.
Makes sense. So at the end of the 3D prompting stage, we have all these individual 3D tiles ready to be assembled.
Almost. There's some post-processing, too. They have to crop out that temporary base, scale the tile to the right size, and rotate it to match the original 2D image. Appendix 8.4 goes into the details of that.
Making sure everything fits together perfectly. So finally, we get to the 3D blending stage. How do they make those tile boundaries disappear?
Even though those tiles are aligned pretty well, there might be some small gaps or bumps where they meet just because of the way Trellis works and the fact that it's only generating from a single viewpoint. So they use a combination of 2D and 3D blending techniques to smooth everything out.
Okay, I'm following so far.
First, they take two neighboring 3D tiles, put them side by side, and render a 2D image of that. Then they use another 2D image generator, called 8-2D, to in-paint the area where the tiles meet, essentially blending them together.
So they're using a 2D generator to paint over the seams in the 3D scene.
You got it. And then they do the 3D blending. This happens in Trellis's latent space. It's like a compressed representation of the 3D data. They take the latent representations of the two tiles and combine them. Then they apply Trellis's processing, but only to that little boundary region. This smooths out the connection in 3D, making the transition really seamless. Usually, they only need to tweak a specific layer in the latent space, the second stage, to get it right.
So it's like they're directly manipulating the underlying 3D data to make it all flow together perfectly.
Yeah, that's the idea. And then, because they might have made adjustments in the latent space and they also cropped out that temporary base earlier, they need to increase the resolution of the 3D data. This is called upsampling.
So they're basically making the 3D data more detailed.
Exactly. But they found that just simply upscaling the latent data can introduce some visual artifacts, like you can see in Figure 9. So they use this more clever upsampling method where they first increase the resolution of what's called an occupancy volume, which is basically a 3D representation of where the object is in space. And then they generate new, higher resolution latent data by showing the original 3D tile from multiple viewpoints.
Okay, that sounds pretty complicated.
It is, but it works really well. It helps preserve those details and textures, as you can see in Figure 9, and the results they show in Table 3.
So they're going through all this trouble just to make sure the final 3D world looks as good as possible.
That's the name of the game.
Okay, so after all this, how does Sin City actually measure up? Does it really work that well?
The results are pretty amazing. They did a study where they had people compare scenes generated by SimCity to scenes generated by block fusion, which was a leading method before this, and people overwhelmingly preferred SimCity. They rated it better for overall look and feel, the quality of the geometry, how interesting it was to explore, the variety of scenes, and how realistic it looked. All of this is summarized in Table 1.
So in head-to-head, Sin City wins.
Pretty much, yeah. And they also did what are called ablation studies, where they remove or change different parts of SimCity to see how much each part contributes to the final result.
So kind of like figuring out what's really important, what's not.
Yeah, exactly. They found that just trying to generate a whole large scene in one go with Flux and then convert it to 3D didn't work well at all. It lacked detail, and they couldn't control things well. You can see that in Figures 15 and 16.
So the tile-based approach is essential.
It is, and they also showed that the 2D prompting context is really important because without it, you get inconsistencies in the size of objects across the scene. Figure 10 shows that pretty clearly.
So each new tile really needs to be aware of its neighbors.
Yeah, and that rebasing technique, that's crucial too. Table 2 and Figure 8 show that without it, the 3D models don't have those nice flat bases and they don't line up properly. And their upsampling method is a big improvement over just basic upscaling. You can see that in Table 3 and Figure 9. And the 3D blending, that's what really makes those seams between the tiles disappear. Figure 12 shows that pretty convincingly.
So they've put a lot of thought into every little detail, and it shows. What about the visual variety? Can Sin City create different kinds of environments, or is it just good at one thing?
Oh, it can create all sorts of things.
Mm-hmm.
The images in their paper and the supplementary material, Figures 1 and 17 through 20, show a huge range from cityscapes to forests to deserts, and they can even control the characteristics of individual tiles to create patterns across the world, like showing a transition from summer to winter across a landscape.
Wow, that's amazing.
It is, and it's not just about static images. You can actually move through these 3D worlds in a consistent way. Unlike some other AI-generated environments where things can sort of fall apart as you try to explore them, figures 11 and 17 show how you can actually move through these SimCity worlds in a way that makes sense.
That's really impressive. It sounds like we're finally getting to a point where we can create truly explorable virtual worlds from text descriptions. But of course, every new technology has its limitations. What are some of the challenges with SimCity?
Well, right now, those tiles can be a bit too rigid. They can create larger structures across multiple tiles, but those structures can sometimes feel a bit blocky, like they're made of, well, tiles. They're working on ways to make those transitions smoother, but it's still a challenge.
So there's room for improvement in how those larger structures are handled.
Yeah. And they also use some heuristics, which are basically rules of thumb, to figure out things like the height of the ground surface and how to remove that temporary base. Those heuristics work well most of the time, but not always.
So there's a chance that sometimes things might not align perfectly, or the ground might be a bit uneven.
It's possible, but it's something they're constantly working on improving. And of course, they're also limited by the capabilities of those pre-trained models they're using, Flux and Trellis. Like, Trellis isn't always perfect at matching the colors and textures from the 2D image, so sometimes those transitions between tiles, even with all that blending, can still be a little bit noticeable.
So it sounds like there are still some kinks to work out, but the overall potential is huge. What are some of the things they're looking at for the future?
Well, one thing is making that tile structure more flexible, maybe allowing tiles to be different sizes or shapes, or to overlap a bit more organically. And then there's something called course-defined modeling, where they could first generate a kind of rough layout of the world and then go back and add all the fine details. That could help make the worlds even more coherent and complex.
Those sound like really interesting directions.
Yeah.
So to wrap up, what makes SimCity so exciting?
It's the first system that can create these huge navigable 3D worlds from text prompts without needing to be trained on any specific 3D data. It's like it's learned how to build worlds just by looking at images and text.
And that opens up so many possibilities for him.
Oh, it does. For game developers, VR creators, anyone who needs to build these virtual environments, this could be a total game changer. It could make the process so much faster, cheaper, and easier.
It could free up so much time for creative exploration and innovation.
Exactly.
It really does feel like we're on the verge of something big. Imagine a world where creating your own virtual reality experience is as easy as typing a description. The possibilities are endless, and it's something we should all be thinking about. To our listeners, if you want to dive deeper into the technical side of SimCity and see more examples of what it can do, we'll link to the research paper in the show notes. Thanks for joining us today. It's been a fascinating look into the future of virtual worlds.
It has. Thanks for having me.
And thanks all our listeners, and see you next time on Science Corner.
See ya.
Bye.
Bye.